Hi, Nick McQuaid here. Welcome to the second of two videos for week 4, normalization. This is the other of the, I mentioned there are two most important subjects, entity relationships, and normalization is the other one. And this is also probably the longest video of the bunch. So let's get started. So as an overview, let's say what normalization is, and we'll also talk about denormalization a little bit too at the end. Normalization is the process of transforming a database so that anomalies are unlikely, if not impossible. And it's usually conducted in phases, which are called forms. And pretty much every database that I've ever worked with has been normalized to at least third normal form. So first, second, and third normal form. And many advance to fourth normal form or Boyce-Codd normal form. And the convention that we're going to observe for writing out relationships is as follows. We're going to have a relation name, and then in parentheses, the columns in that relation. And the primary key will be underlined. The any foreign keys will be in an oblique if it's sans serif, or italics if it's a serif font. And then the other fields will be listed. Now, some books follow the convention that the name of the relation is in all caps. We will not observe, so that this would be in all caps. We won't observe that convention. We'll just observe the underlining and italicizing conventions, which are common. And if you're in plain text without the ability to underline or italicize, one other convention, there are a couple of other conventions that are used. One is to write PK after the primary key and FK after the foreign key. So good news, everyone. Your relation is already in first normal form, um, because whether an item is atomic is a matter determined by people. So SQL has no concept of non-atomic items. Oracle does. Oracle has an extension to SQL that explicitly defines some items as non-atomic. But in any other database but Oracle, any relationship specified, any relation specified in SQL is in first normal form unless that relation was specified using an extension to SQL. Okay, so everything is atomic. So, for example, I talked about a Chen notation diagram that had phone number as a multi-valued attribute. A person could have more than one phone number. That would be a problem to represent because the uh, two phone numbers would be non-atomic. If you had the two phone numbers in one cell, each phone number by itself would be atomic, but the two together wouldn't be atomic. Now, there are a lot of database textbooks that teach that first normal form also eliminates repeating groups. So let's say, for example, that you had the two telephone numbers in separate columns. That would be a repeating group, and a repeating group is non-atomic. So some textbooks harken back to the original definition of non-atomic and move the eliminate repeating groups into a more appropriate place in second normal form. And that's what I would like you to do. Eliminate repeating groups to second normal form, which is usually written as 2NF. So you may specify a relational notation for a table in first normal form without reference to a primary key. For example, this would be in first normal form without reference to a primary key, assuming that every row is unique. If every row is not unique, and every row that has uh, an auto-incremented integer, the row is going to be unique. If you created a primary key, you wouldn't have to specify that it's a primary key, but you would know that it was unique. Okay, second normal form is a relation is in second normal form if it's in first normal form and every non-key attribute is fully dependent on the primary key. So an attribute is fully dependent on the primary key if it's on the right-hand side of a functional dependency. So remember we wrote out those A determines B things in curly braces. And you can write those out for each table and figure out, what's on which side of the functional dependency. if it's the left side, if it's the primary key, or something that can be derived from the primary key using the transitivity of functional dependencies, which we talked about briefly. In many, if not most applications, functional dependencies are implied but not certain. So for example, in real life, Apple, the computer maker, obtains displays for its iPhones from several different suppliers. To uniquely identify a display item might require concatenation of the item identifier and the supplier identifier. Or each item might have a separate identifier that incorporates the information about which supplier provided the item, which is actually how they do it in Apple. Now, suppose we know the following functional dependencies. Supplier determines name, street, city, state, and zip. And suppose further that we know that zip code determines city and state. Then the following item relation is in 2NF. If we have this information about the item. So notice that we have removed. What have we removed here? Oh, we've removed the supplier information. The information that's dependent on supplier is no longer present. So to create the required tables, I would also specify a supplier table, which has supplier, name, street, and zip code as a separate relation. But I don't need city and state because city and state depend on zip code. So I could have a separate zip code and zip code city state. Actually, I don't really need this because you can look this, there's a free database that you can look this up with, supplied by the post office from your tax dollars. You may object to using the same word to identify an entity and an attribute. So here we had an entity called supplier and an attribute called supplier. And you might object to that. We usually add ID to attributes named for entities, but SQL does not require it. And SQL offers us a way to qualify ambiguous identifiers. Here's a questionable functional dependency. What about colors? Is the following functional dependency legitimate? The item determines colors. Well, in fact, in the parts database, it does not. Colors has been described as multi-valued in the ER diagram. Oh, I don't think I showed you the ER diagram for the full parts database. I only showed the stuff that I needed to. Anyway, it should be eliminated from the item relation, and a new relation should be specified as item colors. Item is the identifier, and colors is part of a concatenated primary key, and every row uniquely identifies a combination of item and colors. So there's only one super key, one candidate key, and one primary key possible, which is the two items, the two columns together. Now a relation is in third normal form if it is in second normal form and every non-key attribute is non-transitively dependent on the primary key. So what is transitivity? A transitive dependency exists if a non-key attribute determines a non-key attribute. And we can see this. Here's an aside. The inventor of the relational database said a non-key column should depend on the key, the whole key, and nothing but the key, where the whole key refers to 2NF and nothing but the key refers to 3NF. So here's an example of a 3NF violation. I asked Opus 4.7 for an example of a 3NF problem, and here's what it gave me as a result. Well, I actually edited this quite a bit. So employee and employee ID, name, department name, department location. The employee ID determines the name and department ID. The department ID determines the department name and the department location. So the department determines its own attributes. So department name and department location depend on employee ID only through department ID. See, that's transitive. So department ID is not a super key, and dependent department name and department location aren't prime. So this violates third normal form. And by I'm blanking on what prime means here. I think it means atomic. Uh, oh, aren't primary. That's what it means. They aren't primary. Okay, so this violates third normal form because what's happened here is that we should have a um, a relation that has employee ID, name, and department ID, right? Yeah, employee ID, name, and department ID, and then we have a separate relation with department ID, department name, and department location. Yeah, I think that's right. So I'm troubled by one thing about this. If we do this, how can we have, oh, this is a non-key attribute. This is a foreign key attribute in this table, so this could be null. So this would be okay because we could have an employee who doesn't, a new employee doesn't necessarily yet have a department. So they just have an employee ID and a name. Um, and this could be null because it's not part of the primary key. Okay, so there are problems. If we change the department's location, we have to update every employee row in the department. If we try to record a new department, we can't do it unless at least one employee is assigned to it. And deleting the last employee in a department loses the department's information entirely. So we split it into two relations. Okay, so department ID is a foreign key. Okay, good. And then department ID um, determines name and location. Okay, so now each non-key attribute depends only on its table's key. The decomposition is lossless, joinable back without spurious rows, and dependency preserving. So instead of this relation here, we have two relations, employee and department. Good. So you see that the process of normalization typically involves making narrower but longer tables. So think that the ideal table is tall and skinny instead of short and fat. Okay, Boyce-Codd normal form has the property that if every determinant is a candidate key, then it's also is the left-hand side of a functional dependency, then it's also then it's in Boyce-Codd normal form if it's a candidate key. So Claude Opus gives us an example of this, and I don't have a font for this. This is just an element. Boyce-Codd normal form is an element of third normal form. There's a problem with the fonts when I translated this. So um, a non-trivial dependency, X determines A is permitted if A is a prime attribute, even when X isn't a superkey. So Boyce-Codd normal form closes the loophole. X must always be a superkey. So Boyce-Codd normal form is an element of third normal form. The trade-off is that every relation has a lossless dependency preserving third normal form decomposition, but it doesn't always have a dependency preserving Boyce-Codd normal form one. That's why third normal form is the practical target in most designs. So I'm certainly not going to make you do a Boyce-Codd normal form. And I'm also not going to make you do fourth normal form. Fourth normal form is even more abstract and difficult to understand. So Christopher J. Date, in his Introduction to Database Systems, in which has many editions, Date is the most prolific writer on relational databases, and any of his books are interesting, but many of them are kind of like versions of each other. Anyway, this one, the Introduction to Database Systems, is kind of the main reference work, and he gives this definition of normal fourth normal form. Now, he refers to a relation as a relvar, or a relational variable. So it's in fourth normal form if and only if, whenever there exist subsets A and B of the attributes of R. So these are columns in this table, such that the non-trivial multi-valued dependency A multi-determines B is satisfied, then all attributes of R are also functionally dependent on A. And you can't understand this definition without understanding what multi-valued dependence is. So if R is a relvar, that is a relational variable, that is a table, and A, B, and C are subsets of the attributes of R, then we can say that B is multi-dependent on A multi-determines B, if and only if in every legal value of R, the set of B values matching a given AC value pair depends only on the A value and is completely independent of the C value. Okay, and this, I've actually been in another university. I was required to include this and an exam question on this in class, but I I personally don't use it, so I don't I pass it on to you so you're aware of it, because some people are picky about it, but you're not gonna have to use it in this class. You're not even gonna have to really understand it in this class. Although, if you want to understand it, Date is really good, comprehensive reading. Okay, so the rationale for this is that we're talking about part of data intensive systems. So most computer systems can be considered either data intensive or compute intensive. And in this class, we're only going to consider data intensive systems. And we're only going to consider part of data intensive systems according to Martin Kleppman. This is a great book that you should check out, Designing Data Intensive Applications. Is it a coincidence that it's on page 385? And the other one was also on page 385 of that book? Weird. Um, Systems of record, derived data systems. So the kind that we care about in this class are systems of record. We're less concerned about derived data systems. Oh, and I say that here. Okay. So a system of record, also known as a source of truth, holds the authoritative version of your data. When new data comes in, it is first written here, and every fact is represented exactly once, and the representation is typically normalized. So parts of the fact may be represented in different places, but the fact as a whole is only represented one time. And if there is any discrepancy between another system and the system of record, then we assume the system of record is the correct one. That's the definition of the system of record. So there are also derived data systems like data warehouses, and these are the result of taking some existing data from another system, uh, and transforming or processing it in some way. This got garbled. This There shouldn't be a bullet point here. This should be, the word system should go right here. If you lose derived data, you can recreate it from the original source. And a classic example is a cache. So data can be served from the cache if it's present, but if the cache doesn't exist or doesn't contain what you need, you can fall back to the underlying database. And that's why they tell you to delete the cache if you're having problems in your browser. Denormalized values also fall into this category. So indexes and materialized views, which we're not going to cover, can fall into this category. They can all be recreated from the original source of truth. And in recommendation systems, predictive summary data is derived from usage logs, usually. Derived data is important, but it's redundant. It duplicates existing information, but it's essential for getting good performance in many cases on read queries. It is commonly denormalized. And you can derive several different data sets from a single source, enabling you to look at the data from different points of view. Systems of record and derived data systems work together. Normalization protects the systems of record. They must not have insertion, deletion, or update anomalies, but it's okay for the derived systems to have anomalies. Normalization, and this is because normalization incurs a performance penalty. Joining all these, you decompose one table into many tables, and then joining the tables together takes time. So denormalizing it may speed up its performance, but it risks these anomalies, so you don't want to depend on it. Okay, so that's all I have to say about normalization and denormalization, and I thank you for your attention and look forward to our next week.